All right. Hello, everybody. Welcome back to Math Background for Machine Learning. So today we're going to continue with matrix differentials, which, to remind everybody, matrix differentials are a way to take derivatives that is often a lot more convenient than sort of the, call it the old-fashioned way. So by the old-fashioned way, I mean writing an expression where you have a ton of integer indices into matrices and differentiate yij with respect to zkl and try and keep track of all of the indices. So that's the old way. The new way is basically to directly work with a Taylor series. And so last class we talked about the notation for representing this Taylor series, and this class we're going to do a bunch of examples of how to work with it in that representation. So to remind, we had a Taylor series that looks like this. So the change in y is approximately equal to a of x hat times the change in x. So just to type check, for each fixed value, so this is a Taylor series, it's for each fixed value of x hat, the point that we build the Taylor series around, we have the change in y is a linear function of the change in x. And of course, it's a potentially nonlinear function of the point where we build the Taylor series. And we had a more compact notation, dy equals a of x dx. This means the same thing. It's basically saying that we just have the linear part of a Taylor series for expressing the change in y as a function of the change in x. And so here we've written x for the point that we evaluate the Taylor series at, and dx for the change in x. All right. And so we had an example of squared error. So if we have a vector b in some vector space and a linear operator a, we could try and find the x such that ax minus b norm squared is as small as possible. And to do that, the first step would be to take the derivative of y with respect to x, right? So we could do it the old-fashioned way, which I've written out here, or what we're going to talk about today is how to do it in this differential notation, which will, in only a couple of lines, get us that the change in y is a linear function of the change in x, and the coefficients of that linear function depend on x. All right. So as always, please ask questions on Piazza, and we'll try and answer them for everybody. All right. And so the key point of doing it this way is that there are going to be some derivatives that are a lot easier to find using the new notation and methods compared to the old. We'll hopefully see a few of those, but it's going to turn out that there are some derivatives that we're interested in doing that you can't easily even write in the old notation, right? So there's no for example, if you have a matrix valued function of a matrix valued input, if you think about that, you could have the derivative of the ij component of the output with respect to the kl component of the input. So that's 4 indices, and the derivative would be a 4-mode tensor. And we don't have sort of nice ways to write that down. By comparison, we'll see some examples of this where we can easily write down the expression using matrix differential notation. I should point out, as always, it's a good idea to do type checking to make sure you understand an expression. And so let me talk about what the types are going to be. So we'll have some equation that looks like, a variable f is a function of some other variable x. F could be in some vector space, u could be in some other vector space. And so this here is describing a function that maps a vector in u to a vector in v. right? And so the differential then will have two vectors in U, x and the change in x, and it'll map those to a vector in V, which is going to be the change in F, right? And so we'll write an abusive notation. Sometimes we will write f of x instead of f equals some expression of x. In other words, we'll use f to mean both the function and the output of the function. And in any given expression, it's going to mean one or the other. Hopefully it'll be clear from context which is which. And the reason I bring this up is that both of these notations are common, right? So it's common to write either this, f equals that, or f of x equals that. Same thing with here, it's common to write either df equals the right-hand side, or df of x semicolon dx is equal to the right-hand side. All right, and another bit of notation confusion that's good to keep straight is that if you take df of x, right, this means the differential of the expression f of x. Whereas if you have df of x semicolon dx, right, so if you have two arguments instead of one, right, then df is referring to the function, the differential, right? And again, this should be clear from looking at the expression, because if you've just got the x argument, it means you're about to take the differential of the function f of x. And if you've got two arguments, it means you have already taken the differential, and df is that differential. All right, so it's just a couple of points about notation to keep straight. I should also point out that most of the examples we do are going to be with one variable, but it works just fine to have Taylor series where you have two or more input variables. So here's a real function of two real variables, and its differential is going to be then a real function of four real variables, x, y, and the change in x and the change in y. And just like before, it represents a Taylor series. This is the Taylor series. Another bit of notation as well that's going to be useful is a prime. So a lot of times people write f prime for the derivative of a function with respect to its argument. And there's a way to relate this to the differential, is that the differential of f at x and dx is always going to be f prime of x times dx, right? And the reason we can do this is that we know the differential is always a linear function of dx, and then the slope of that linear function is f prime. And I guess when you read an expression like this one here with both x and dx in it, we're thinking of x as a fixed point, the point at which we're building a Taylor series, and then dx is a variable which is describing how the change in x that we're working with in the Taylor series. Same thing for matrix valued expressions, right? So if we have df is a vector and dx is a vector, then a of x could be a matrix, b of xy could be a matrix, and we could have a differential expression like that one. All right, so we've said a few times that the most important tools for working with differentials are linearity, the chain rule, and the product rule. So let's go through what those look like in the differential notation. So linearity is pretty easy. We basically just have a differential pass through multiplication and addition. Right, so meaning multiplying by a constant. So if you have a and b are constant, then d of ax plus by is a dx plus b dy, or d of a sum is the sum of the differentials. This rule actually follows from the product rule if you use the fact that the differential of a constant is 0. All right. So The next rule is the chain rule. So if you have two functions, f and g, and f goes from a vector space v to another vector space w, g goes from u to v, then you could have a function f, you can compose these to get f of g of x, and the differential of that is written this way according to the chain rule. So f prime of g of x, dg of x. And so this this expression here on this side uses a bunch of the shorthands that we've used. So let's unpack those shorthands. And to do that, let's write u for g of x, right? So then here, this left-hand side is the differential of f of u. And by the chain rule, that's f prime of u du, right? Or equivalently, df of u and du, right? These are equivalent. Then if we take this and substitute back in g of x for u, we get d of f of g of x is the differential of f applied at g of x and d of g of x, right? So, right, du is d of g of x. And then we can expand this differential, right? D of g of x is dg of x and dx, right? And so d of f of g of x is the differential of f applied at g of x with the change argument equal to the differential of g at x and dx, right? And so here, right, this is sort of the shorthand form. And here, this is the longhand form. All right. Right, so there's a question about x and x hat. So let's go back to the point where we talked about that, right? So we had a Taylor series where we have two separate variables, y and y hat. Y hat is the point that we're going to build the Taylor series around, and x is the new point that we're going to evaluate the Taylor series at. And now we're changing variables to get to this expression. So here, instead of x hat and x, we're going to have x and the change in x, right? And so here, in this expression where we have x and x hat is where we're evaluating the Taylor series. Here, x is where we're evaluating the Taylor series. Here, the change in x is x minus x hat, and here the change in x is dx. So the difference between these two expressions is basically a change of variables, right, from x and x hat to x and dx. And as well, just the fact that we're interpreting this, that we've gotten this into the differential notation. Right? So this is basically just a change of variables coming here. There's another question on Piazza. And so the question is whether you get a unique answer by type checking. Yes, every expression should have a unique type, right? And you should be able to figure out for every sub-expression of your expression what that type is. You may have to, if you're type checking an expression that appears in a paper or a textbook or something like that, you may have to yourself give names to some of the vector spaces that are not explicitly named in the textbook. But once you've done that, everything else is going to follow. All right, so keep those questions coming on Piazza. All right, so basically what we've just done is the chain rule, which has actually, this should be a very familiar form of the chain rule here, that if you take the ordinary derivative of f of g of x, that's f prime of g of x times the derivative of g, right? And here the difference is just that we're using the differential operator instead of the d by dx operator, for example. However, when you're trying to understand this expression, it might help as well to write it out in long form, which is this. By long form, I mean the one that uses the explicit differential functions that are something like df of x and dx. And so this here is equivalent to this long form. And again, it's worth type checking, right? So if we look here, df is going to be a function that takes vectors, two arguments in vector space v, x and dx, and maps them to w. And we're composing df with g and dg. And g and dg both have outputs in v, so we can do that composition. And then finally, here dg expects two arguments in vector space u, which we're providing as x and dx. And we should note as well that it's pretty easy to see that this expression here is linear in dx, right? Because you're taking dg is linear in its second argument, and then you're taking a linear function and putting it in the second argument of df, which is again linear in its second argument. And so you compose two linear functions to get a linear function. All right, so that's linearity and chain rule. Last one is product rule, and then we'll see some examples. So first, let's do the version of the product rule for matrix multiplication. So if you have f of x is g of x times h of x, and here times is just matrix multiplication, then the product rule is that df is equal to dg times h plus g times dh, right? And so again, that should be a familiar form for product rule because it looks very much like the scalar version of it. You can also extend to three or more terms, right? D of f times g times h is df times g times h plus f times dg times h plus f times g times dh, right? So that's the version for matrix multiplication. The interesting thing is it actually is the exact same rule for any what I'll call a multiplication-like operator. So a multiplication-like operator is an argument that's linear in each of its arguments separately. By that, so a function like that is sometimes called bilinear if it has two arguments, or multilinear if it has three or more. So matrix multiplication is bilinear. So is composition of linear operators, so is ordinary scalar multiplication, inner products of vectors, including dot products, but like lots of more unusual operations are bilinear as well. So for example, cross product of vectors is component-wise product of vectors or matrices or tensors. Kronecker product, Cauchy-Rao product, right? Like these are all, these last few are operations that we haven't ever mentioned in this class, but they're operations that you'll sometimes see in papers or textbooks. And as long as they're bilinear, you know that you can use the product rule. So for example, if we write a small circle to mean the Hadamard product, the component-wise product of two vectors or matrices or whatever, then the differential of the Hadamard product of f and g is the differential of f Hadamard g plus f Hadamard differential of g, right? And so, you know, every multiplication-like operator has a product rule like this. The main difference from the product rule that you are familiar with is that in some of these cases, the multiplication-like operator is not commutative. So for example, if you do matrix product, you have to be sure not to reorder the factors in a product because a times b is not necessarily equal to b times a. So other than that, it's just like using the scalar product rule. So there's a question on Piazza. In the product rule, how is the mapping of vector spaces decided for G and H? I'm not sure I understand that question. So if someone can expand on it a bit, But if we take, oh, do you, I guess the question is just for me to type check this, this expression. That makes a lot of sense, so let's go ahead and do that. Right, so we have a function g, which is in v to w, and we have a function h, which is in u to v, right? And so so actually we can make this, I think, even more we can make this even more general, right? So let's actually make it more general. We'll make x in one of these in a different vector space, x to y, right? And so then let's say as well that w is equal to r m by n, and y is equal to something that you can multiply with rm by n. So let's make that r. So let's say n by l. Okay. So now the expression g of x multiplied by h of y, right? So that means that x is in v, y is in the vector space. Oh, I shouldn't have used x and y because I'm using them. Why don't we, we'll call them here a and b. Right, b is in x, and then g of a is in r m by n, h of b is in r n by l, and then this whole thing is in r m by l, right? So that expression type checks. And then we said that right, this is then going to be f of a comma b is equal to that, and so we can say that df is equal to product rule, right? So dg of a times h of b plus g of a dh of b, right? And so so what do we want to do here, right? So the output so again, dg of a is going to be in r m by n. H of b is still in r n by l. G of a is going to be in r m by n, and dh of b is going to be in r n by l, right? So each one of these expressions is r m by l, right? So this whole thing is r m by l, and again, this whole thing is going to be r m by l, m by l, right? And so the whole thing, when you add them together, is going to be an r m by l, which is good because then you can add them together and get that the type of DF is going to be a matrix in R m by L. So that's an example of how to type check a product rule. And like I said, this is actually a little bit more general than the example that I gave in section 7 here. So I think maybe after class I'll update section 7 to have the more general version. Let's see, so there are some more questions appearing. Some specific examples of multiplication-like operators. I mean, there are a bunch of examples here, right? So for example, cross product of two vectors, right? So U cross product V. You would have, or Hadamard product, right, is this example right here. Right, so somebody's pointing out, again, that I generalized here, right? So I gave A and B as separate arguments to G and H, whereas in this example I used the same argument for G and H. That's one of the reasons that this is more general. So that's why I'm planning to update 7 to include something more like this after class. Let's see. Shouldn't the function h map to v? No. The function h has to map to some vector space that's compatible in terms of matrix multiplication with the output of G. Right, so we're doing matrix multiplication of G of A and H of B, and so the only thing that's required is that G of A have a second dimension, n, that's the same as the first dimension of H of B. All right, so somebody's pointing out a potential error in yes, right. It looks like there's an error in the lecture notes. I dropped a sign, like a minus sign. Thank you to somebody for pointing that out. I'll fix that afterwards. I apologize. I apparently forgot how to take scalar derivatives of trig functions. Yes, sorry about that. All right, I think that's all of the questions on the lecture notes on Piazza. So let's keep going. All right. So we had sum rule and product rule and linearity. And so now I want to give an example of taking a derivative of a simple expression using these rules, right? And so our expression, we're going to use the same example that we did before, which is just the squared error between ax minus b. And we're just going to use the identity that the norm squared of some vector z is z transpose times z, right? So here we have that y is equal to ax minus b transpose times ax minus b over 2, right? And so to evaluate that, right, we have that dy is equal to, by the product rule, so let's just pull out the half over here, and we'll have d of ax minus b transpose, right, with the parens like this, times ax minus b, plus then ax minus b transpose d ax minus b, right? So that's the product rule. We take d of the first times the second plus the first times d of the second. And then when we expand this out, we know that transpose is a linear operator, multiplication by a constant matrix A is a linear operator, and so we just push the D inside. And D of a constant B is 0, so we'll get 1 half A dx transpose times ax minus b plus ax minus b transpose. D of ax minus b is again just dx, right? Sorry, a dx. Let's make that neater. And then we can collect terms because this is a scalar and this is a scalar, and the transpose of a scalar is itself. And so we can just take the transpose of one of these terms without changing it, and we realize that the terms then become equal. So it's twice the term, which cancels with the half, and that's just equal to a x minus b transpose a dx. Okay, and so here I've done this out in a lot of detail. I would ordinarily skip a bunch of these steps if I were doing it for my own purposes, but I've written them out because it's good to follow all of those steps. And in just a few steps, we did, and with sort of much less ink, we did the same thing that we did at the end of the previous set of notes, but we did it in the differential notation as opposed to in the old-fashioned d by dx notation. All right. Let's see, so why are the dimensions of d of g of a and g of a the same? So g of a, the dimension is the output dimension of g. And so, we could call that, let's say, y equals g of a. And then the differential dy should be the same dimension as y because it represents a change in y. It represents something we can add to y. And so the dimensions of dy and y are the same, which is the same as saying the dimensions of d of g of a is the same as the dimensions of g of a. All right. Cool. All right, so coming back to the squared error example, we said that one of the reasons we might want to take the derivative of squared error is to minimize it. So if we want to minimize the squared error between ax and b, we want to set the differential of ax minus b norm squared to 0, and that's going to find us the x such that ax is as close as possible to b in the sense of minimizing the squared 2 norm. And so to do that, to minimize, we set the derivative to 0, and in particular we set the differential to 0. And so, right, if we say that 0 is equal to dy, that's the same as saying 0 is equal to this expression here. The only way for this expression to be 0, remember dx is a variable, so for it to be has to be 0 for all values of dx, and the only way for that to happen is if this matrix here is 0. So that's the same as saying that 0 is equal to ax minus b transpose times a. And if we multiply that out and rearrange, that's the same as saying a transpose ax. That's you take the transpose of this expression, right, because transpose of 0 is 0. A transpose ax has to be equal to a transpose b, right? And so this is a system of linear equations, and we can solve that system to find the x that minimizes ax minus b norm squared. This system of equations is called the normal equations. And we talked in a previous set of lecture notes about how to solve linear systems, and all of those methods apply. For example, we could take the LU factorization of A transpose A here, and then do back substitution to find the best value of X. And I should point out that for a symmetric positive semi-definite matrix, LU factorization is simplifies. It becomes Cholesky factorization, which is to say that the U matrix is the transpose of the L matrix, so it's L times L transpose. All right. So in this expression, somebody's asking why some term can be dropped. So let's see, we dropped, so b is a constant, so the differential of b is going to be 0. Right, so here d of ax minus b transpose, the d is going to go through the transpose, because transpose is linear. It's going to go through ax to be a dx, and then through, when you take differential of b, that's 0. And so the differential of ax minus b transpose is just a dx transpose. I think that's the term that the question is asking about. Oh, and then so somebody is asking why these two terms are equal. So let's see. A times dx is a vector. Ax minus b is a vector. So vector transpose times vector. This is a scalar. Same thing here. And so for any scalar, right, like 3 transpose is equal to 3. So the transpose of any scalar is just the scalar itself. You think of the scalar as a 1-by-1 matrix. And so when this term is equal to its own transpose, and when we take the transpose of this term, we get that term. And so that's why the two terms can be collapsed into one. All right, cool. So that's an example of how to use differential notation to solve a very simple minimization problem, right? We have a quadratic function, the squared norm of the difference between ax and b, and we take the differential of it, set the differential to 0, and we get a set of linear equations. And this is something that you could have done using the old notation, so it's not necessarily a perfect example of the benefit of the new notation, but it is at least a little bit shorter than doing it the old way. And we'll see in a bit some examples that are much harder to do using the old notation. All right, so let's move on to the next set of lecture notes. So we have a bunch of examples of differentials here. So the first couple of examples are generalizations of this least squares problem. So you can basically go through fairly similar math, just a little bit more complicated, and make sure that it all makes sense. So what if, in the normal equations, what if A transpose A is non-singular? What if A transpose A is singular? Right? So then if A transpose A is singular, you're not necessarily going to be able to solve for, whoops, sorry, this should be A transpose AX is equal to A transpose B. Again, I'll fix that. So your question is, what if you can't solve for X because A transpose A is singular? So I guess the first question is, does it even have a solution? And the answer is yes, it does, because it actually has infinitely many, because the range of A transpose A is going to include A transpose B. But so we could, if we wanted to, just say, okay, let's see if we can find one of the infinitely many solutions. But what I'm going to do is something a little bit different. I'm going to change the problem a little bit. I'm going to say that in addition to minimizing the squared norm between ax and b, we'd also like to minimize the squared norm of x. And so what we want to do is we want to minimize this function here, which it's just a linear combination of the original thing that we were trying to minimize plus lambda times the norm squared of x over 2. And so we've got a coefficient lambda here. And if the coefficient lambda is 0, we get back the original problem. This term vanishes. And if we make lambda really large, that means we're paying a lot of attention to trying to keep the norm of x squared small. And doing that is called regularizing the solution. It's going to turn out to be important in machine learning in a bunch of ways later, but for now you don't need to worry about that. You just need to think about this as a new problem that we want to solve. Right? And so solving this problem should now be very straightforward for anyone who followed the previous example. So let's just go through. Right, so the first thing we're going to do is just write out an expression for z by turning norm squared of a vector into vector transpose times vector. Right, so that's this and this. We did that for 2 copies of norm squared, and then multiplying out everything just to keep just so that we do things in a different order and get a slightly different example of how to work with differentials. And again, I've brought together B transpose AX and AX transpose B. Those are the same term because they're both scalar and they're the transpose of each other. And so we get 2B transpose AX. All right, so we have, we'll start from there, that Z is equal to 1/2 X transpose A X minus 2B transpose AX plus X transpose, sorry, that's a transpose, X transpose X plus, sorry, let's do it in the same order. So B transpose B, and then plus lambda times X transpose X, right? And so dz is equal to, we'll just push it through every linear operation, right? And so we'll get 1/2 d of x d of this thing, right? And we'll use the product rule for that. So that's dx transpose A transpose AX plus X transpose A transpose A dx minus 2 B transpose A dx. Differential of B transpose B. B is a constant, and so this is a constant. Its differential is 0, and now we're at lambda X transpose X, and again, product rule says that's lambda dx transpose X plus lambda X transpose dx. All right, and to avoid writing lots of parentheses, I'm going to use the convention that the differential has very high precedence. So for example, here, this term, it's dx and not d of x transpose x. So if I were to write the parentheses, it would be like this. Right? All right, and so now we can collect pairs of equal terms, right? So this is a scalar, this is a scalar, they're transposes of each other, so we can collect them. This is a scalar, this is a scalar, they're transposes of each other, so we can collect them. And then we can, include the half, and so we'll get dz is equal to A transpose A dx, right? That's these two terms, minus B transpose A dx plus lambda X transpose dx, right? And if we want to, we can factor out dx, right, using that x is equal to the identity times x. So you get is equal to A transpose A plus lambda identity dx minus B transpose A dx. All right, and so that is, and then if you set that equal to 0, you get this expression right here. And you can solve, that's another system of linear equations that you can solve using Cholesky factorization. And the nice thing about this one is that as long as lambda is bigger than 0, this system is guaranteed to be non-singular. In other words, A transpose A plus lambda I is guaranteed to be invertible. All right. All right, so somebody is asking again about the derivative of the transpose operation. So for every linear operator, differentials pass right through it, right? So multiplication by a matrix is linear, so the differential of AX is A dx. Transpose, as it turns out, is a linear operator. In other words, the transpose of 3 times A is 3 times the transpose of A. And so because of that, differential passes right through transpose. So the differential of A transpose is the differential of A transpose. All right. So here's yet another example of a least squares problem. We're going to do it a different way just to again, get a slightly different version of the example, exercise your math in this area once again. And so for this version, we're going to say what happens if the matrix A is wider than it is tall, right? So that's going to make A transpose A be a singular matrix. And just to give a name to it, we're going to say that A is in R m by n with m smaller than n. And so the normal equations version, right, where you solve an n by n system of equations, if n is really big, that could be expensive. Like, you know, solving a million by million system of equations could be pretty expensive. And if m is like 100, it's going to turn out that we can use this this other formulation called the Gram matrix formulation, and we'll only solve a 100 by 100 system of equations. And so that's going to be much more efficient. And so to get there, we actually don't even have to take another derivative. We could set it up that way if we wanted to, but we can just derive it from this version here by multiplying both sides of the matrix by A. And so that's what we get here. Multiply it out, and then pull out AX on the right. And so we're going to now substitute and say that U is equal to AX. So what is U, right? So what we're trying to do is minimize the squared error between AX and B. And so if we take U equal to AX, we're going to try and minimize the squared error between U and B. And so U is the best approximation to B within the span of the matrix A. Or the regularized best approximation. And so this means now that we have a different set of linear equations that we can solve for U, and as long as we're happy getting U instead of X at the end, we can solve an m by m system of equations instead of an n by n system of equations. And if m is 100 and n is 1,000,000, one of those is obviously a lot easier to do than the other. And again, we do it by the exact same technique we use, for example, Cholesky factorization and back substitution. And just to go back and give you more practice with infinite dimensional vector spaces, we could think about the case where A, instead of being a matrix, is a linear operator from an infinite dimensional vector space V to Rm. So in that case, we can represent A as using a bunch of vectors in V. So AX is going to be, the first component is going to be the inner product of A1 with X, and so on to the mth component being the inner product of AM with X. That's a general representation of a linear operator that maps V to Rm. And in this case, the Gram matrix is just going to be the matrix whose ij element is the inner product between AI and AJ. And after that, everything works just like it did before. And so the nice thing about that is that we can solve for U in this case using an m by m system of linear equations, just get a finite dimensional representation, even though X and A both dealt with this infinite dimensional vector space V. All right, so let's do one last example, which is a neural network. So this is not going to be a general neural network, but it's going to be a two-layer neural network. So let's write this out, right? So we have inputs X, and that's going to be in let's say Rn, right? And then we're going to map those to something in we'll call it U1, which is in Rm. And the way we're going to do that is we're going to take a linear function of x. So W1x plus b is equal to U1. That's a U. And my writing is messy today. There, okay. And then we'll say, okay, U2 is in RL, and we're gonna say that W2 times G of U1 plus, sorry, this should be B1 and this B2. We're going to call that U2. Right, so here W1 is going to be a matrix, which is in Rm by n. B1 has to be a vector in Rm. Here W2 is going to be a matrix in RL by m. B2 is going to be a vector in RL. And to make it a neural network, G is going to be what's called a component-wise nonlinearity. So that means, so U1 is a vector in Rm. G is going to map Rm to Rm. So let's actually write that. G is a function that maps Rm to, Rm to Rm, and it's going to be a diagonal or component-wise function, meaning that the ith output of G, the ith component of the output of G depends only on the ith component, the same component of the input of G. And so an example would be a function like this, right? So that looks like, right, if we just draw a set of axes, that's going to be a function that looks like this. It's nearly linear here. It's nearly linear there, and it rounds off between it with a smooth nonlinear function. So this is, if you know what a rectified linear unit is, this is a smooth version of that, right? And then finally, I guess I should say that y is in RL, and it's equal to, y is equal to f of U2, and f is again a component-wise nonlinearity. And so I should write, just to be complete, f is a function that maps RL to RL. All right, so if you're familiar with neural networks, this is a fairly standard two-layer, fully connected neural network. If you're not, you don't have to worry about it. All you have to do is say, well, this is an example of a complicated function that maps a vector in Rn to a vector in Rl, and we're going to differentiate it. But I see there are some more questions here, so let's look at them. Oh, okay. So somebody's asking why back up here in regularized least squares, why is this matrix here non-singular? That's actually somewhat subtle. And you don't actually have to know the answer to this, but I'll give you the answer just because it's interesting. So A transpose A is a positive semi-definite matrix. Every matrix of the form matrix transpose times the same matrix is going to be positive semi-definite. That's fairly easy to prove. When you take the singular value decomposition of a positive semi-definite matrix, right? So let's do that, right? So if you have A transpose A is equal to US U transpose, the SVD, right? And the diagonal elements SII are going to be greater than or equal to 0, right? And some of them could be 0, and in particular, if A transpose A is singular, then some of the diagonal elements will be 0. If we now say then that A transpose, let's move that up, say that A transpose A plus lambda times the identity, right? If we write that, that's equal to US U transpose plus lambda times the identity. But one way to write the identity is U times U transpose, because an orthonormal matrix is its own inverse. And so this is equal to U times S plus lambda I times U transpose. And here, right, every diagonal element is going to be strictly greater than 0, right? Because it was greater than or equal to 0 before, and adding lambda I just adds lambda to every diagonal element. And so U is invertible because it's orthonormal. S plus lambda I is invertible because every diagonal element is bigger than 0. And U transpose is invertible because it's orthonormal. And so that means that because all three of those component matrices are invertible, this matrix here is invertible as well. So that's why A transpose A plus lambda I is guaranteed to be non-singular. Let's see. Oh, to set, I see. That's there's another question here. So when we set dz, so here's dz, right? This expression here, and when we set dz to 0, right? So dx is a variable; it can be anything. And so the only way for this expression, dz, to be 0 all of the time, no matter what dx is for the coefficients of dx to sum to 0, right? So here the coefficients of dx are A transpose AX minus A transpose B plus lambda x, right? So A transpose AX, A transpose B, and lambda x, right? And so if those sum to 0, that's the only way for this expression always to be 0 no matter what dx is. All right, so that's the end of questions so far. So let's go back to our neural network, right? So we have this complicated function y is equal to f of, this stuff, right? And it implements a 2-layer neural network. And so we can actually very very easily take the differential of this function using chain rule and linearity, right? So dy by chain rule, right? So y is f of u2. So dy is f prime of u2 times du2, right? And then d goes in through the linear operation. So w2 dg of this plus, b2 should vanish. I apologize for that. So let us we'll write this out, and I'll change it again after class. So dy is equal to f prime of u2 du2 is equal to f prime of u2 times w2 dg of u1, and then the b vanishes. The b2 vanishes, right? And so then this is equal to f prime of u2 times w2, and then dg of u1 is going to be g prime of u1 du1. And we'll just write that out, right? w1x plus b1, right? And then this is equal to f prime of u2, w2, g prime of u1, w1 dx1, right? And so in this expression here, just to type check, right? So x1 is the, dx1 is the same, sorry, not x1, just x. And so dx is the same shape as x. So that means that it is a, going back up here, right, it's a vector in Rn. W1 is an m by n matrix, right? We've got that here, so we can multiply that. G prime of u1, right, so u1 is a vector in Rm. G is a function that maps Rm to Rm, and so its derivative is an m by m matrix. It happens to be a diagonal matrix because it's a component-wise function. So G prime of u1, that's an m by m matrix. We now, at this point here, have a vector in Rm. We multiply by u2, which is an L by m matrix, and we get a vector in Rl. And then f prime of u2 is going to be then an L by L square matrix, which is diagonal because f is a component-wise function. And so at the end, we get something the same shape as y, which is a vector in Rl. And so we successfully type check. All right, so so that's a few different examples of how to take differentials of some useful machine learning related functions. And again, for all of these, it's fairly, the derivation is fairly straightforward and nice compared to writing everything out component-wise, which is much more error-prone. All right. So the last thing that we will probably have time for today, we'll see, is so I gave a bunch of rules so far for working with differentials. And those are the key ones. They're the most important ones to remember. There are a lot of other identities that involve derivatives and differentials. And so rather than trying to memorize all of them, it's good to just, have a table, look them up in a table. The most common table that people use is called the matrix cookbook. And so, if you ever run across an expression involving, the differential of, let's say, you know, the cofactor matrix or something, right? Like some weird expression. Look it up in something like the matrix cookbook, right? Rather than trying to derive it yourself. However, a word of warning, whenever you use a table of identities, you have to make sure that you really understand the notation, because there's lots of cases where the subtle differences in notation can make you get the wrong answer. All right. So there are a bunch of identities that just point out that some operations are linear, and these are, you know, operations that you'll commonly run across. So we already ran across that transpose is linear in the least squares example. Matrix trace. So the matrix trace is the sum of the diagonal elements of a matrix. It's not immediately obvious why that's an important operation, but we'll see in a second that it is. And it's linear. So the differential of a trace is the trace of a differential. And then the last thing is that reshaping a vector or a matrix or a tensor into a different shape, that's a linear operation, right? Because basically, you know, if you just move entries into different spots, then those new entries are the same as the old ones, and therefore they're linear in the old ones. Maybe one of the most common things, the most common way to reshape something is to take a matrix and string it out as a vector by stacking all of its columns together, right? So you take a square matrix and you pull off its first column, and then the second column and stick it there, and the third column and stick it there into a big long vector. That operation is often called vec, and then the inverse operation of taking the vector and pulling off the, you know, pieces of it and stacking them back together into a matrix, that's called unvec. MATLAB and NumPy both have functions, notations to deal with vec. So MATLAB uses m of colon for vec of m, and Python uses ravel, numpy.ravel. All right, so back to trace. The trace is the sum of the diagonal elements of a matrix, and you can see from the definition that it's a linear operator. If you take twice a matrix, that's going to be twice the trace. And the key reason that trace is important is that I guess there's a couple of reasons, but one of them is that the trace of A transpose B, if you work it out, it's the sum of a useful inner product in that vector space is going to be the trace of A transpose B. The other thing is that it has some nice identities that make it convenient to use to manipulate corresponding elements of matrices A and B, and so that means that it's effectively a dot product between two matrices. And so that means that if you're working with a vector space whose vectors are, you know, n by m expressions, and so, for example, if you have a scalar, which you think of as a 1 by 1 matrix, then the trace of that 1 by 1 matrix is just the scalar itself. We already, the trace of the transpose of a matrix is just the same as the trace of a matrix, because transpose doesn't change the diagonal elements of a matrix. And then this one is surprising to a lot of people the first time they see it. If you have two rectangular matrices A and B, such that A times B is square, so n by m and m by n, for example, then the trace of A times B is equal to the trace of B times A. And again, not obvious, but if you work it out using the definition of matrix multiplication and trace, you can see it fairly easily. And so that's a useful trick for manipulating expressions involving differentials, because you'll often get, for example, you take a scalar like the you know, like a scalar objective function that depends on a bunch of matrix variables. You replace it by the trace of that scalar, you take the differential, and then you rotate terms to get to isolate the, let's say, dx and dy by themselves. All right. And then there are, the last thing I want to mention is that matrix inverse and matrix determinant come up fairly often, and there's an identity for taking the differential of the inverse and of the determinant. So two things. What is the determinant? We haven't described it before. There's a lot of different ways to define it, but one way to define it is if you want the determinant of a matrix A, you take the LU factorization of A, and you take the product of all of the diagonal elements of L and U. Not clear immediately why that's an important operation, but for example, it shows up in the likelihood function for a Gaussian distribution. Right, and so here are two formulas involving the differential of an inverse and of a determinant. And again, you probably shouldn't try and memorize these formulas. You should just write them down or look them up in a table of identities if you need them. And another one that comes up often is the log of a matrix determinant, and that actually has a nice simple expression as well. All right. So there's lots of other identities for other functions of matrices, but these are going to be maybe the most frequently used ones that I've shown so far. So I should point out that let's take this first one, the differential of the inverse. This is a nice example where it's hard even to write down the derivative. So if you think about it, let's say f is an n by n matrix. df is also then going to be an n by n matrix. The ordinary derivative, therefore, is going to be an n by n by n by n, right, 4 copies tensor. And that's going to be just a pain to write down. But we've got a very simple expression here for the matrix differential, right? So this is much, much nicer to write down than any expression that you care to think of that involves a 4-mode tensor. All right. So people have been working with derivatives for a while, and so there's a lot of special names for different types of derivative. So as far as we're concerned, they're all differentials, but just to map back to things that you may have seen before, if you have the differential of a scalar is equal to a times the differential of another scalar, a here is the ordinary derivative ds by dt, right? If you have a scalar s, so s is a function of a vector w, the differential of f is going to be a vector transpose times the differential of w, which is also a vector. So this vector v is called the gradient, right? So we have a real valued function of a vector argument, and its derivative is called a gradient. The other way around, if we have a vector valued function of a real argument s, the gradient is called the tangent to the curve v as a function of s. If you have a vector function, dv is a matrix times dw, where v and w are both vectors. The matrix M is called the Jacobian matrix of that vector-to-vector function. Yeah, and so, these 4 here, right, all have sort of counterparts in ordinary, I guess, calculus before anybody came up with a differential notation. And so they all have different names, but they're really all the same concept. They're just different instances of a matrix differential. And because people came up with them completely separately and then unified them later, there's 4 different names for these concepts. And then these other entries in the table, right? So you could have, for example, here, a matrix function of a matrix argument. You can't, in general, write that in ordinary derivative notation unless you want to write out a 4-mode tensor. But you can perfectly well handle it in differential notation. For example, this example here with the inverse. And there's not a name for it because people had not gotten around to writing it out and studying it before somebody came up with a matrix differential notation. All right, so everything here where there's a dash is something where it's hard to write it out in ordinary notation. If you had to, before you knew matrix differential notation, what you would do is you would take a matrix and string it out as a vector, right? And then differentiate with respect to that strung out vector. So you'd be using vec and unvec a lot, but that can get ugly pretty quickly. All right, so I think we have time to get at least a little way into second differentials before in the next 4 minutes. So just as a review, right? So we had an operator f that went between vector spaces u and v, and we took the differential of f, and that was an operator that took 2 arguments in u and gave us an output in v, right? So the arguments in u are x and dx, the point at which you make the Taylor approximation, and the increment for the Taylor approximation, and then the output is the change in f as predicted by the Taylor approximation. And this function is linear in the dx argument. So a specific example of this would be that u and v could both be real vector spaces. Then the differential would take the form a of x dx, where a of x is a matrix. And this was the long notation, so we could also have the short notation df is equal to a of x dx, meaning we can use df to represent the output of the differential function rather than the function itself. All right, so for second differentials, right, what that means is we're just going to differentiate again. So we're going to take the differential of df with respect to its first argument. And so that's called the second differential, d squared f of x and dx. And as the first differential was a linear function of x, the second differential is a linear function of dx. The second differential is a quadratic function of dx. So let's do that in a little bit more detail. So we have d of f of x is df of x and dx. We'll fix dx equal to u for some vector u. So we get, and then we can define g of x to be df of x and u. So g of x is just this differential here with the argument dx fixed to some vector u. So g of x is a function just of x, and we can take its differential, d of g of x, so that's dg of x and dx, right? And then we can say, okay, the second differential of f at the point x in the direction u is going to be dg of x with dx equal to u. In other words, we're going to supply the same u that we fixed as the dx argument of df. We're going to supply that same u as the dx argument of dg. And that's what makes the second differential a quadratic function of dx. So to make that maybe a little bit more concrete, let's say that u is Rn and v is r, so f is a function from Rn to r. df is going to be a function from 2 values in Rn. It's going to be of the form a of x dx, where a of x is a gradient, and it's a row vector. And then when we take d squared, we're going to get something of this form. dx transpose a of x dx, capital A here is a square n by n matrix. Okay, so the reason we'd want to use a second differential is to get a second order Taylor approximation, but I think we're basically out of time, and so we'll continue with second order Taylor approximations next time around. My office hours start now, go until 3:30 as usual. And again, feel free to keep asking questions on Piazza. All right, cool. I will see you guys next time.